Hi, I'm Halle Doenitz. I'll be a first-year graduate student this fall in the Department of Civil and Environmental Engineering. This summer I'm doing research with Professor Victor Lee in the Advanced Civil Engineering Materials Research Lab. My research topic this summer is the self-healing of restrained shrinkage microcracking in M45-ECC and electrical methods for detecting damage. ECC stands for Engineered Cementitious Composites, also known as bendable concrete. ECC is reinforced with polyvinyl alcohol fibers and is very ductile. ECC performs well under tension, making it useful for seismic resistance in high-rise buildings, also used as link slabs and bridge decks. One property of ECC is its ability to self-heal. ECC has a tight crack width, about 50 microns in diameter, due to fiber bridging. These cracks may heal themselves at the surface by hydration and carbonation through wetting and drying, reducing maintenance costs in the field and improving durability. This is a picture of an ECC coupon subjected to flexural bending. As you can see, ECC can withstand more strain before failure than normal concrete. Shrinkage is a loss of volume in cementitious composites due to evaporation of water and hydration of cement particles. Cracks may form when these cementitious composites are restrained from shrinking and not allowed to shrink freely. This is very common in the field. Non-destructive damage detection is imperative to the safety and stability of a structure. This is typically done by visual inspection in the field. A focus of my research is to utilize the electrical properties of ECC to detect damage. ECC is a semiconductor, and resistance will increase with damage or cracking. My research this summer focuses on self-healing of restrained shrinkage cracking and monitoring the damage along the way through electrical measurements. The first thing I did in my experiment was mix and cast ECC specimens around a steel ring, formed by a 14-inch cardboard tube form, removed after 3 days. This is where I am right now in my experiment, waiting for the shrinkage cracks to form before I take them off the steel ring. This induces restrained shrinkage cracking, about 0.15% equivalent tensile strain. Next in my experiment, I will allow the specimens to self-heal through cyclic wetting and drying. My proposed cycle is 24 hours submerged in water and 24 hours to dry. Electrical impedance spectroscopy is the electrical method I will be using to monitor this damage. EIS measures impedance, which is the opposition to an AC current, through a medium over a range of frequencies. These impedance measurements will be taken across the specimens after each wet-dry cycle to monitor the level of self-healing. The outer two copper strips will pass the current, while the inner two strips will pick up the impedance across the specimen. I anticipate that the resistance will decrease over time due to self-healing, and the conductivity will increase due to the healing of the cracks. In conclusion, my research will verify that restrained shrinkage cracks in M45-ECC will self-heal under cyclic wetting and drying. I will also implore the use of a relatively new non-destructive damage testing method, which is EIS. Our department's website is acemrl.engine.umich.edu, and I can be reached at denitzh@umich.edu for any questions. Thank you.